You can read them.
Okay, welcome everybody. This is our CBE 4 review for Calc 1. Should say Math 1210 or Calc 1. So hopefully you're in the right place. This is being recorded, just the screen, and I won't say names or anything, but it'll also be posted to the Aggie Math YouTube channel, just so you know if you want to watch it. It should be posted soon. But I'm Walker, I'm a recitation leader.
I'm Connor, I'm also a recitation leader.
So, yeah. Oops. Let's see if I can turn the page here. There we go. Okay, so CBE 4 covers lessons 11 through 13, differentials, mean value theorem, and extreme values. But really on the CBE, it's only testing extreme values for the most part. Everything else is kind of being used in the background. So for extreme values, the first topic we have is our absolute minimum and maximum. And we call the maximum value of f if there is some c so that it's greater than all other f of x. So basically, the absolute maximum or global maximum is greater than all other values of f. And the same with the minimum, it's lower than all other values of f. Pretty simple for that one. The tricky part is going to be the local maximum and minimums. Critical numbers. You guys remember what critical numbers are without looking at the screen? Yeah.
That's our domain range, and it's also points where our derivative equals 0.
Exactly. Points. So points where our derivative is equal to 0. So f prime of x is equal to 0. There are a few more critical points as well if we're looking on a closed bounded interval. Does anyone remember? Those are the main ones that we think of, but there are a few more. I guess we can read this. So if our derivative is equal to 0, or if our derivative is undefined. It's important to check there because on a graph, like you might have a point that's like a sharp edge where the derivative is not defined. But if you look at that graph that I just drew, that is a global maximum. So you should also consider that. And then don't forget, the derivative is not defined anywhere at the endpoints. So you should also check. Those are also critical points that we consider. And the reason we care about critical numbers is our maximums will occur at a critical number. Any questions on that? Okay.
Okay, so what do you guys think? Where are the critical points on this graph? Have it in your brain. Okay. So always include the endpoints. So here at -2 and here at 4 are our critical points. Is there anywhere where the derivative is not defined except for at those endpoints? Okay, we're defined. Okay, and so where are the other critical points at? -1, and why is that?
The derivative equals 0.
Awesome. So whenever our derivative equals 0, so at -1, at let's say 2, and at 3, we also have critical points. So we have a total of 5 critical points on this problem. Is that right? That looks right. Okay. I don't know
Okay.
if it is.
Okay. So remember we use the extreme value theorem a lot. If f is a continuous function in a closed and bounded interval, then f achieves an absolute maximum and minimum in the interval. And it's going to either occur at the endpoints or the critical number. So So basically, if f is continuous, we do have a max and a minimum. So to find these absolute maxims, mins, I guess we have a 3-step process if you want. Find the derivative, and then find all critical numbers, where f prime of x is equal to 0 or undefined. And then for absolute max and mins, we don't really need the first derivative test and the second derivative test, if you remember that. We just need to plug it in and see which one's the highest and lowest. It's pretty easy for max and the absolute or global maxes. So example problem 2 says find the x coordinates for the absolute maximum and minimum of the following graph. This is a more conceptual question. What would you guys say is the absolute maximum? I saw, what did I see? A 3.
Or you -3, I guess.
Negative 3, okay. X is equal to -3. Because that corresponds to this, which is definitely higher than all other y values. What about an absolute minimum? I think I heard -4, because this is lower than all other values. So if the CBE asks for the absolute maximum, what would you guys say? This is a play on words, and I want to make sure you guys get it right.
Just find the x coordinates, so it would be -3 for the absolute maximum.
Okay, so if it asks for the absolute maximum, it's actually asking for the y coordinate. I'm hoping that it will be clear. In this problem, it says find the x coordinates. It might ask where does it occur. That would be an x coordinate. But if it asks for the actual actual max, you're gonna plug in the y value. So that'd be like 41 or negative, I don't know, 5 or something for this problem. So I just don't want you guys to get tripped up. But so if it asks for an absolute max or an absolute min, you're probably going to be plugging in the y values. If it asks for where it occurs, plug in where the x value occurs. Any questions on that? It's a silly thing to get tripped up over, but it happens. Okay, problem 3.
Okay, so now we don't have a graph, we have a function. It's going to be the same process. So it says find the absolute minimum of this function on an interval. So we know right away 2 of our critical points. -3 and 3. But we also have other critical points. Those points on the graph where our derivative equals 0. So we're going to, well, it tells us, find the derivative. So f prime of x I'm going to use the power rule. Bring down the 3. Subtract 1 from the exponent. Same thing here. Is that right for the derivative? Is that what you guys got? Okay. Now I'm interested when this equals 0. So I'm going to do a little bit of factoring. So I'm going to think to myself, what adds to 1 and multiplies to -2? Positive 2 and -1. Thanks, Walker.
Yeah.
Okay. And so my critical points are 2 and -1. No, I make that mistake every single time. This still equals 0. My critical points are -2 and +1, because those are the values that make it equal to 0. This is a mistake I see a lot, that I make almost every single time I factor. Okay, so we have 4 critical points. And we're going to plug them all into the original and see which one yields the lowest value, which hopefully it tells us. Okay, so hopefully we can all do that on the CBE, plug them into the calculator. Apparently the solution, if we plug in 1, we get 35/6, which is the lowest value that we would get if we plugged in any of the critical points. Any questions about that? Okay. Good. Okay.
Okay. Okay, so problem 4 says find the absolute maximum of the following function on the interval 1/2 to 2. It's 1/2 there. Okay. What should I do first? Find critical points? How do I find critical points?
Take the derivative.
Yeah, we're gonna need the derivative. So what do you guys get for the derivative? Yeah, I heard 3 minus x to the negative 2, or 3 minus 1 over x squared. That's just a power rule because f can be written as 3x plus x to the negative 1. So hopefully that's not the thing tripping you up on this CBE. So is this derivative undefined anywhere? I heard maybe a it is undefined at x equals 0. Of 0 is not defined. But do we care about x equals 0? It's not in our interval because it's 1/2 to 2, so we don't really care about it. We could also say, well, the original function's not defined there, so we don't really care about it either. So that's not really a point we're going to be considering. What about f prime of x is equal to 0? What if we set this equal to 0? What do we get? Okay, we got to do some algebra, so we can add 1 over x squared to the other side. So you get 3 is equal to 1 over x squared. There's a few different ways you can do this, I suppose. I'm going to multiply by x squared on both sides. 3 times x squared is equal to 1. Or x squared is equal to 1/3. X is equal to plus or minus the square root of 1/3. Is that what you guys got? Did I make a mistake? Cool. So we got 2 critical points from there. Do we care about both of them? No, I'm seeing some head shakes. Negative 1 over root 3 isn't in our interval, so we don't really care about it. So the only critical points that we care about is x is equal to 1 over square root of 3, positive 1. And actually, do we care about this one? Yeah, I think we might. Do we? I think so. Maybe not. I think they changed the question on me. It might not be supposed to be a 1/2. Let me see what the answer is. I think they changed the question on me. This is awkward. It shouldn't be this hard. I think there's a number wrong, but 1 divided by 3. Let's see. How do I erase here? 1 divided by root. Where's my pen? One divided by square root of 3 is less than. Oh wait, no, it's greater than 1 divided by square root of 4. Okay, so we can plug that in. So it is in their interval, right? Okay. So that is kind of a harder check than we needed to do, but that's one critical point we can consider. Okay, how do I find the absolute maximum then? Just plug all our critical points in. All right, and the boundary. I'm gonna include our endpoints in our critical points as well. So f of 1 over square root 3, f of 1/2, f of 2. At this point, you can use your calculator. And I mean, I won't show it because now you have a calculator on the CBEs, but if you plug in 2, you get the largest value at 13 halves. Any questions on that one? Yeah.
Would you not use 0 as a critical point and solve that as well?
Okay. Why do you say 0 is a critical point?
Because I thought we said it was undefined.
Right. So the derivative is undefined at 0, but notice that we're only concerned with the maximum in this interval.
Okay.
So 0 is not in the interval, so we don't really care what it is at 0. Does that make sense? Yeah. Any other questions? So once you find your critical points, make sure that they're in the interval. This one it took a little bit of effort to make sure that it was in the interval, but and then plug them all in to get your absolute maximum. Okay, now we're going to talk about local mins and maxes.
Okay, it's the same, but you can have more than one. For example, sine has an infinite number of local mins and maxes. Here's a local max, here's a local max, here's a local max. Here's a local min, here's a local min, here's a local min. Okay? Are there any questions about that? You only care about what's close. As long as it's bigger than everything right next to it, it's a local max. So, to find local min and max, they're going to correct critical numbers, but not necessarily. If it's a critical point, it doesn't necessarily mean it's a min or a max. But if it is a min or a max, it is a critical point. That's kind of confusing, but yeah. So the first method is the first derivative test, and we're going to use f prime to determine if f changes from increasing to decreasing or vice versa. And then the second method is the second derivative test where we measure the concavity. And so essentially the second derivative test is we find the critical points using the first derivative, plug those critical points into the second derivative, and that will tell us the concavity of our critical point. I think it makes more sense just to do an example. So, yeah.
Just like kind of what you said before, just because the derivative of 0 doesn't mean it's a local min or max. Would that mean would that just be where it kind of has a plateau and then
Yeah.
goes back?
I'm trying to draw it, but I'm not good.
Okay, yeah.
So just imagine that the derivative is 0 there. It's not a min or a max.
Yeah, okay.
Right? Does that make sense? Okay. And so there's a second derivative test. You'll plug in your critical point into the second derivative. If that outputs a negative value, that means that your function is concave down, which means you have a max. If you get a positive value, it means it's concave up, which means it's a minimum. I like to use the hands. Positive, negative. Positive, negative. Okay. So, looking at the graph, is f double prime of 0 less than 0? Is it negative, positive, or equal to 0? So right here, at this point, is that concave up or concave down? Down, right? Okay. At this point right here, is it concave up or concave down?
0.
Concave up, right? What about right about here. Let's imagine I drew it at the perfect spot where it's changing concavity. It's neither, it's an inflection point. So the second derivative would be 0 there. Okay, so that's the second derivative test. You take the derivative, you find the roots, you plug those critical points into the second derivative, and that'll tell you the concavity at that critical point. Okay? And this is for local min and max. Any questions? Okay. It's negative. What we got? Okay.
All right. So problem 6 says to find the x coordinates for the inflection points of the following function. F of x is equal to 2x squared plus 5x plus natural log of x. And this one has a few steps for us. First of all, why does it say, why should we find the second derivative? It says that as a first step, but why do you guys think we should do it?
Because you're finding your inflection points.
Inflection points will occur where the second derivative is equal to 0. Okay, so you guys got to help me out here. F prime of x is equal to
4x plus 5 plus 1 over x.
4x plus 5 plus 1 over x. I agree. And then the second derivative, f double prime of x, would be what? I heard it. 4 minus 1 over x squared. Again, just use the power rule, rewriting the 1 over x as x to the negative 1. Okay. Do you think we can find where this is equal to 0? I think we can. We can do it. Okay. Same thing as the process of the last one. We can add 1 over x squared to the other side. So we get 4 is equal to 1 over x squared. Multiply both sides by x squared. So x squared is equal to 1/4. And x is equal to plus or minus the square root of 1 over 4. Remember, it's division or multiplication inside the square root. We can distribute it through. So we get plus or minus 1 over 2. Because the square root of 4 is 2. Are we good on that one? Okay. So here's some potential inflection points. Should we just call those good and move on? Why not? Yeah, you.
You have to plug them back in to see, right?
Yes. So yeah, you're exactly right. I mean, there's a tricky one with this one, but notice that if the second derivatives, I'll give you a function here, f of x is equal to x to the 4th, which looks like kind of like a funky parabola, basically. Then f prime of x is equal to 4x cubed, and f double prime of x is equal to 12x squared. So at 0, the second derivative is equal to 0. So you think, oh, it's an inflection point. But notice on this graph here, it doesn't actually change concavity. So we need to double check that it does change concavity for the function. It's kind of like the critical points. Everywhere it's 0 is a critical point, but it's not necessarily a local min or max. Everywhere where the second derivative is 0 is not necessarily an inflection point. So we need to double check that it actually changes concavity. So I could set up my number line, and I could plug in something in this interval, and this interval to double check, see what the concavity is. Well, so I don't know. There's a few different ways you could do this. You could plug in -1, or you could plug in -1 billion and just kind of see what it's doing. I propose doing 0 in the middle interval And for the right interval, you could do 1 or 1 billion or whatever you want to do. So f double prime of -1 is equal to let me do over here, f double prime -1 is equal to 4 minus 1 over -1 squared. I think that's 3. Which is greater than 0. So our second derivative is greater than 0, which Connor uses his hands. I just think if my second derivative is positive, then I have a positive smiley face. This guy's happy. If my second derivative is negative smiley face, which is concave down. So positive, so we're concave up in this interval, and f double prime of 0 is, we can't plug in 0. 0 is usually a good choice, but we can't plug in 0 for this one. We could do 1/4. How does that sound? All right, 1/4 is between -1/2 and 1/2. Oops. F prime of 1/4 is equal to 4 minus 1 over 1/4 squared, which is equal to 4 minus 1 over 1/16, which is 4 minus 16, which is definitely less than 0. So it's negative in this interval, so it's kind of concave, so it's concave down. And then you can do the same thing for f double prime of 1, which is 4 minus 1, which is 3, which is greater than 0. So at first it looks like it does change concavity at -1/2 and 1/2. Do you guys agree? Okay. This is a fun problem because if you look at the original function, where is this function defined? Basically, the only thing that we have to worry about is natural log of x, right? That's the only thing that might happen. So if you remember, natural log of x is defined anywhere from 0 to infinity, but not including 0. So -1/2 is not an inflection point because we can't even plug that into the original function. So this is a fun problem because it looks like you get 2 inflection points, but the domain isn't even negative, so we only take the positive one. And we confirmed that it does change concavity. Is there any questions on that? I'm assuming that the CBE will be a lot simpler than that. In fact, on the CBE, it does usually tell you there is 1 inflection point, find it. Or there is 2, find them both, or usually it's just 1. Okay.
Okay. We're gonna find concave down. So, first derivative, 4/12 x cubed minus x squared minus 3x. Is that good? Is that right? Equals 0. Okay. Interesting problem. How would you guys go about solving this?
First, don't we have to find the second derivative?
Yes, but what are we going to plug into the second derivative? No, it's okay. So we can right now. Might as well do them both at the same time. Bring down the 3. I'm going to get x squared minus 2x minus 3. It's the best way to do this is to find the inflection points because I don't want to solve the roots for the okay. I have not done this problem before, so I'm doing this for the first time.
Connor subbed in last minute, so.
So I was scared that we were gonna have to find the roots of f prime But thankfully, all we care about is the intervals for which the function is concave down. So we can solve for the inflection points and then check. Because the inflection points are where we will potentially change concavity. So thankfully, we can just ignore the first derivative. Now we can use our factoring rules. What multiplies the negative 3 and adds to negative 2? Negative 3 and positive 1. So our roots are x equals 3 and x equals negative 1. And so those are our inflection points. Our potential inflection points, technically. So now, just like Walker did in the last problem, we'll draw a nice number line and label our inflection points. And then test on both sides of these inflection points to see what's happening. We know for a fact that the concavity will not change on the interval from negative infinity to negative 1. Because there are no inflection points between there. For the concavity to change, there has to be an inflection point. So the concavity can only change at negative 1 and 3. So if we plugged in negative 2 into here, into the second derivative, we would get, here, I'll do it up here. F double prime of negative 2 equals negative 2 minus 3 times negative 2 plus 1 equals negative 5 times negative 1 is 5. Is that right? Correct? So from negative infinity to negative 1, our function is a happy smiley face, concave up. Okay, now let's plug in 0. In this case, we can plug in 0. 0 minus 3 times 0 plus 1 equals negative 3. So from negative 1 to 3, we're concave down. And lastly, if we plug in 100, we can plug in anything we want. We're going to get 100 minus 3 times 100 plus 1 equals 97 times 101, which is positive. That's all we care about. So the interval in which we are concave down is from negative 1 to 3. Hopefully that's right. Yahtzee. Are there any questions about that? So in the case that you don't want to find critical points because it's hard, or you don't want to, you can just find inflection points and test on intervals. Okay? Yeah.
Okay. Okay, problem 8 says if f of x is continuous at all x, and if f prime of 3 is equal to 0, and f double prime of 3 is less than 0, then which of the following statements must be true? Okay, what can you tell me about x equals to 3? What do we know for sure? Yeah.
Well, because f double prime is less than 0, that means it's concave down.
Okay, so that tells us it's concave down.
Yeah, and because the derivative equals, the first derivative equals 0, that means that it flattens out there.
Yeah, exactly. So it's a critical point, and it's concave down, so it lies something like that. So f of 3 has to be a local maximum, right? Let's say B. Nice. Okay, problem 9 is very similar. True or false, if f of x is continuous at all x, and if f prime of 37 is equal to 0, and f double prime of 37 is equal to 0, then f of 37 must be a local extrema. Okay, I see some head shakes. Why do your head shakes? Head shakes.
0, but it's not at, it's at an inflection point, so it's just like a we did at the beginning.
Yeah, it might look like something like that. It might be an inflection point. In fact, it probably is. But in any case, we can't say what it is. Since our second derivative is equal to 0, inconclusive. We know nothing. Back to square one. It's kind of a bummer, but yeah. So we don't know. So f of 37 must be local extrema? No, that's false because we don't actually know if it is or not. Questions on that? I think on the CBE, it'll say like not enough information to determine or something.
I think it's CBD. Cannot be determined.
Oh yeah, cannot be determined. That's it. Yeah. Okay.
This.
Yeah, if you want to.
I mean, I don't care.
It's up to you.
I can just.
Okay.
How many local minimums and maximums do the following functions have? Walker's gonna do this one.
Okay. I'll do this one. This is a little tricky. Okay, so f of x is equal to x to the fourth plus 4/3 x cubed minus 8x squared minus 16x plus 7. Let's work with that one first. Okay, local minimums and maximums. What should I do? Yeah, let's find the derivative and set it equal to 0 to find where local maximums would occur. So f prime of x is equal to 4x cubed plus 4x squared minus 16x minus 16. Is that what you guys get? Okay, and we want to find where this is equal to 0 for critical points. It's defined everywhere, and so we're good. We just want to look for where it's 0. Okay, does anyone remember factor by grouping? Yeah. Okay, we're going to factor this by grouping. So I think we can pull a 4x squared. You don't even have to know the name. Just start doing things. We can pull a 4x squared out of the first few terms. And then we get x is all that's left of 4x cubed plus 1. Remember. And let's double check. If I multiply this through, I get 4x squared. So that's 4x cubed plus 4x squared. Okay, we're good. I think we did that right. I know we did that right. Excuse me. Oops. Okay. There we go. So I can also pull a negative 16 out of the next two. So I'm going to pull up minus 16. That leaves me with an x plus 1. Does everyone agree? And then I have 4x squared of something minus 16 of that same something. So I can just say, or combine like terms and say it's 4x squared minus 16 of our x plus of our something, or x plus 1. Or you can pull out an x plus 1, however you want to think about it. I think I can factor this even more. If I pull out a 4, get x squared minus 4 times x plus 1 equals 0. And that's a difference of squares. So x plus 2, x minus 2 times x plus 1 equals 0. Okay, so our critical points are x equals 2, negative 2, and negative 1. Cool. Let's use the second, I don't know, we can use whatever we want. But let's try using the second derivative test to classify this. We want to see which one of those are local maximums and which are local minimums, or neither. So what do you get for f double prime of x? Let's see. I think we get 12x squared plus 8x minus 16. Okay, got some nods. Must be right. Okay. So what does the second derivative test mean or do? Like, how do we use the second derivative? Most people know they need to find the second derivative, but don't know what to do with it. Plug what values into it?
Plug your value or critical.
Our critical points. Yeah, let's just throw our critical points in there. So f double prime of I don't know. We'll start with 2 is equal to 12 times 2 squared plus 8 times 2 minus 16. Is positive. So, because it's 12 times 4, which is 48. And then, okay, so what does that mean about the point where x is equal to 2? I'm gonna call it a local something. Local what? I'm hearing min, right? Since our second derivative is positive, we have a smiley face, so it is a local minimum. Okay. I got a room here. We'll do f double prime of -2 next. That's 12 times -2 squared. Ooh, there we go. Pen's dying on me, I think. Plus 8 times -2 minus 16. That's still 12 times 4, which is 48. Minus 16, which is minus 32, which is definitely bigger than 0. So what about that point x is equal to -2? Yep, another local min. Whoa. Okay, my pen might have died. Okay, my pen died. We'll use my finger. Okay, and then let's classify our last one. F double prime of -1 is equal to 12 times -1 squared. Plus 8 times -1 minus 16. That's 12 minus 8 minus 16. That's definitely negative, right? You can plug it into, or, you know, I guess it's 12 minus 8 is -4 minus 16 is -20. So it's definitely negative. You can use a calculator if you want. So what does that mean about -1? Local max. Excellent. Okay, how do we feel about f? That's just f. Try that. Yeah, I don't think so.
Does anyone have an extra one that they would be willing?
It's an Apple Pencil Pro.
Just this item.
It's okay. Okay. How about g of x? Let's find out how many local max and mins does g of x have. That's for our second one. And that is correct. We'll see if that's correct, I guess. But okay. What should I do first? Find the derivative. G prime of x. What is that? 15x squared minus 60x plus 60? Which you can, and we want to know when that's equal to 0. So we can pull a 15 out and we get x squared minus 4x plus 4. Which is x plus 2 squared. Excuse me, it's minus 2. X minus 2 squared. So x is equal to 2 is a critical point. Agreed? That's our only critical point. So let's check it using the second derivative test. G double prime of x is equal to 30x. If I just differentiate g prime of x, 30x minus 60. What if I plug in 2 to there? Get 0, yeah. G double prime of 2 is equal to 0. So what do I do? Do I say it's a saddle and it's not? Or like a saddle point, kind of like a plateau? And it's not a local max or a min? Can I say that? No. 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 Remember, if the second derivative is equal to 0, inconclusive. You can't say anything. So what can we do?
Check points around it. Or you could just-
You could check points around it. We could have a word. Some people call it the first derivative test. Good job. Oops. I'm going to erase the stuff we did for F. Okay. So, draw myself a number line. This is how you use the first derivative test. So x is equal to 2. So we're talking about the first derivative here. And we want to know, what does it do? Does it change from decreasing to increasing? If so, if it was negative and then positive, that means the original function is decreasing and then increasing. And it would be a local minimum. Whoa, wrong button. Okay. On the other hand, if we have positive and then negative, that would mean that the function is like increasing and then decreasing and would have a local max, right? Okay. So let's see what it's actually doing. Ooh. Drive me nuts. Okay, we're good now.
I don't know if that'll work. Let me just try it real quick.
Okay, go ahead.
Just like.
Okay. Thanks, Connor. That's okay. It's fine. Okay, so let's check what the first derivative. I don't know. Should we plug in? Hey, oops. Talking about G here. I don't want to erase again. Sorry. So G prime of 0, we can plug in that, right? So what do we get for G prime of 0? Yeah, exactly. It's greater than 0, so it's positive. Okay, what about G prime of...
No.
Oh, thanks
Well,
anyway.
let's go try it.
We're good.
Have fun.
Thanks. What do you guys want to plug in right of 2? 3. Oh, you're so boring. Just teasing. You're not boring. I would plug in 300 if I were you, but it's fine. So G prime of 3 is equal to 15 times 3 squared minus 60 times 3 plus 60. 15 times 9 minus 180 plus 60. 15 times 9. I guess you guys have a calculator, so you could probably figure that out. It's 150 minus 9 minus 15. What'd you say? 135? 135 minus 120? Negative 180 plus 60 is negative 120. So that's greater than 0. Whew. Okay. See, if we plugged in 1 billion, we could have avoided that. Just teasing you guys. Okay, so this is also positive. So what can we say about x is equal to 2? Yeah, it's a saddle point. It's increasing, then it's 0 all of a sudden, then it's increasing again. So it's neither a local max or a local min. Let's see if we can actually get this thing to turn now. Right when I don't want to. Okay, F has 2 local min and 1 local max, which is what we got. And G has no local extrema. Questions on that? I think it's easiest to jump to the second derivative, and then if that fails, use the first derivative test. Okay, so You can also visit the Aggie Math Learning Center for tutors. Also, this website is pretty cool. Has past CBE reviews and some really cool resources on that. But yeah.